Good morning, Year 10. I thought I'd make a video for you guys, just doing a bit of an overview of the topic that we've just covered, which is pressure, which is the last topic in the forces branch of paper 2. Okay, so the idea of pressure. So pressure is very closely related to force. The basic idea of pressure is that when a force is exerted on a surface, then pressure is caused. And the idea of pressure is almost analogous to the concentration of the force. So what do I mean by that? Well, you guys hopefully know the equation for pressure. And the equation for pressure looks like this. You have the force and you divide it by the surface area that the force is being applied on. So the basic idea in this equation is that the concentration of the force, or the density of the force upon the area, is the pressure. And pressure is measured in pascals. That's the SI unit. And hopefully you guys already know that the SI unit for force is the Newton, and the SI unit for area is meters squared. Now, the idea of pressure applies within all of the states of matter. Now, normally we talk about a pressure being exerted on a solid. So when we think about solids, the main idea we think about when we say that pressure is exerted by one solid, so one object on another, is about whether the object, so is the object blunt or sharp? That's the key idea. So when we talk about pressure being exerted by an object, one object on another object, a common example, for instance, is the idea of something like a knife versus something like a surfboard. So a knife will break through a surface because the contact area, which is the edge of the blade, is very small. Okay, whereas a surfboard has a large contact area. So when you're riding on a surfboard on the surface of the water, it's more difficult to break through the surface. Okay, so that's the idea of a solid object exerting pressure on something else. Now, when we talk about fluids, the idea is a little bit different. When we talk about fluids exerting pressure on a surface, so fluids exert pressure on solid objects, we think about the idea of whether the area of contact is large or small. Now, this is almost the reverse. If we've got something like a knife has a small contact area and therefore it exerts a large pressure. But fluids exert their pressure on a surface area. So if the contact area is large, you get a larger pressure, whereas if the contact area is small, you get a smaller pressure. So I'll talk about these ideas a little bit more, particularly the idea of fluids, because that one's a little bit more complex. I hope everyone understands this equation fine. I don't think I need to go into that in too much detail. We have covered it before. So I think I'll probably skip straight to the idea of static pressure. Now, most of the textbooks don't really call this idea static pressure. They call it the pressure in a fluid due to depth. Okay. Now, the reason they do that is that there are kind of two contributing factors to pressure in a fluid. Okay. Now, just quickly, I'm going to make sure I clarify, that a fluid is either a liquid or a gas. The only property of a fluid that has a real impact in terms of pressure is the idea of density. So I'm going to put that alongside here, because lots of people confuse the idea of liquids and gases being a fluid, but really they behave in a very similar way, liquids and gases. When we think about pressure, the property that's important of the liquid or the gas is the density of the liquid or the gas. Because both liquids and gases can flow and move around, it means that they can exert pressure. So static pressure is the pressure inside a fluid due to depth in a fluid. Now, you don't have to know how to derive it, but it's worth being able to derive it. So I'll just walk you through the derivation. Okay. At least in terms of derivations, it's fairly simple. So we imagine a column of a liquid. So this is filled with a liquid, and the liquid has a weight, and therefore it exerts a force downwards, which is the weight of the liquid. The surface area at the bottom here, we're going to call A. And the height of the column, or the depth, I'm going to call H. Also important in being able to derive this is the idea of the density of the fluid. It doesn't matter whether it's a liquid or a gas. This derivation works the same. So what we need to do is figure out the pressure due to depth. So what we'll do is we'll look at the pressure exerted on the bottom of the column of liquid. Okay, the bottom of this container. Now the pressure, let's start off in the right way, is equal to the force divided by the area. The force that this liquid exerts on this surface area is the same as the weight. So this is W. Now the weight is equal to mass times the gravitational field strength. And you also know that the mass of a column of liquid is equal to the density, rho, times the volume, V. So what we do is we plug this into this equation. Okay, so the weight is equal to mass times gravitational field strength. That's equal to rho times V times G, like that. Now V isn't particularly useful here, but we can identify V in terms of two of these variables, because the volume of this container is simply the height of the container multiplied by the surface area. Hopefully you know that from maths, how to calculate the volume of a cylinder. Therefore, if I plug that in, I'm going to put over here, V is equal to H times A. I'll plug that into my equation and we drop out the form that's useful for us. Weight equals rho times H times A times G. So that's what the weight is equal to. And what we want to calculate is the pressure. And actually, we've essentially done all of the legwork of our derivation. So what the pressure is, and I'll plug this equation now into that. Pressure, or static pressure, is equal to the force, which is the weight. So I'll write it, rho H A G, divided by the contact area. So the contact area is the surface area here. So it's A. And hopefully you can see now, all we do is we eliminate the A's. So static pressure is equal to rho H G. Now, two of these things are fixed. Rho, the density of the fluid, doesn't really change. At least when we're talking about liquids, we'll say that rho doesn't change. G is a constant on Earth. It's about 9.81 newtons per kilogram. And H here is the one variable. So what we identify here is the idea that pressure is due to depth in a liquid. So if I double the depth in a liquid, I will double the pressure. So this is the important bit of our equation. I won't use the black pen, I'll use the red one. So that's the idea of static pressure. And you drop out this equation. So rho, normally people write it rho GH for static pressure. And what it tells us is that the pressure in a fluid is due to depth, at least the static pressure. So what does that mean? It means, you know, the typical examples that people use are the idea that if you get a bottle, you get a bottle of liquid, and I think I got you guys to do this, and you pierce holes in it. Let's say you pierce lots of holes at the same depth, and then let's pierce a few holes at different depths. And what you're meant to understand is that the holes at this depth will all push water out in a stream that looks a bit like this. But if you go to lesser depths, so higher up in the bottle, the stream of water comes out more like this, and so on as you go up. The basic idea being that the higher the pressure, the further the stream of water is pushed as it comes out of the bottle. And that just means that you get this pattern forming if you pierce the holes when the initial depth, let's say the water's up here, is the same. Hopefully you realised when you did the experiment that when you pierce holes at the same depth, all of those holes will have the same streams of water coming out because they're at the same depth, and therefore the liquid inside is at the same pressure. So that's the idea of static pressure. It's pressure due to depth. The next idea that you came upon in the course was atmospheric pressure. Atmospheric pressure is just a specific example of static pressure. So I'll write that. So on the last page, we wrote an equation which looked like this. Static pressure is equal to rho G H. And actually, when we talk about atmospheric pressure, it's just the pressure in the atmosphere due to depth in the atmosphere. So that means, let's take an example, might help, okay? Let's say we're on the surface of the Earth. Let's do some little countries. Okay, so we're on the surface of the Earth, and if you imagine the atmosphere is this thick, if we're here on X, we've got a column of air that stretches up in the atmosphere. And the atmosphere is, you know, relatively deep, at least, you know, compared to the kind of altitudes that we talk about on the surface of the Earth. It's about 100 miles thick. And so what you've got to imagine is that when you're standing outside or when you're anywhere on the surface of the Earth, let's say you're at X, you've got 100 miles of air above you, the weight of which is pushing down on you. And, you know, you might not think that air's density is that significant. But if you think about, I'm looking around in my room, which is a room that's about 3.5 meters by about 4.5 meters, the weight, sorry, the mass of the air in this room is about 40 kilograms. Okay, so when you think about the column of air above you, actually that has quite a large weight. And in fact, atmospheric pressure at the surface of the Earth, okay, and that's one, is it PSI? No, apologies, it's 1 atmosphere, is equal to about 101 kilopascals. So that's 101,000 pascals. So that's pretty large. In fact, the pressure due to the depth in our atmosphere is large enough to have lots of interesting and useful impacts. Okay, so a way to visualize this or imagine this is if I stuck out my 2 hands like that, hopefully you can see that, okay, the force on my 2 hands due to the atmosphere is about the same size as twice of my own weight. So it's like I'm carrying one Mr. Breckenridge on this hand and one Mr. Breckenridge on that hand. Now, that might sound a little bit silly. It doesn't feel, when you walk around and you feel your hands, it's not like there's loads of weight on your hands. The only reason it doesn't feel like that is because, well, the atmosphere is pushing on the back as well. And that means that it generally balances out. It doesn't always balance out though. So the effect of suction is due to atmospheric pressure. Okay, a good example is when you breathe. When you breathe, your diaphragm at the bottom of your lungs pulls down your lungs to expand them. And when the lungs expand, the pressure inside drops. And as the pressure drops, that means that the pressure outside, due to atmospheric pressure, is larger. And so air is pushed into your lungs. So anytime you've ever seen suction, that's, you know, the most powerful Dyson suction that you've ever seen, or the air intakes on a jet engine, or when you watch that action film and someone gets sucked out of the plane because a door is blown off, that suction effect is because the atmosphere is pushing on that person. Okay, all of it. And so actually it creates quite a massive force. We talk about it specifically because atmospheres, for instance, are used as a unit for pressure. So we talk about the pressure in atmospheres changing as you change altitude. And sometimes what they do is they do questions. This is, you know, a rather significant mountain, where they talk about a pressure change due to an altitude change. So as you go up, I'll put H as height. As you go up a mountain, the pressure, the atmospheric pressure changes. Okay. Now, it might not feel like if you were going up a short mountain, the pressure would change that much, because actually the atmosphere is 100 miles thick. But actually, the layer, the part of the atmosphere where you get the biggest change in atmospheric pressure is right at the bottom. The reason being that air is not like water. Water is incompressible, and that means as you go deeper, the density doesn't change. But as you go deeper in the atmosphere, density increases. And it increases significantly. Okay, so the pressure at an altitude of, let's say, 10 miles is massively smaller than the pressure at an altitude of sea level. Okay, so, those are the basic ideas of atmospheric pressure. The last thing that you guys learnt about was, and I'll write up here, the idea of flotation and upthrust. So, flotation. Now, hopefully you've heard about a guy called Archimedes. He, can't remember if he was I think he was ancient Greek. I can't remember if he was ancient Greek or ancient Roman. But he apparently, so the story goes, is that he was asked to figure out a way to identify if a gift given to the king or the emperor was really made of gold. The ruler had been told that this gift was made of gold, and so the story goes that Archimedes needed to find out what the density of the metal that this gift was made out of. And so he had to try and figure out a way to calculate, because they knew that the density equation, okay, so density, rho, is equal to mass divided by volume. Now, they had a very simple way to measure the mass, but they had no way to measure the volume of irregular shapes. And so the story goes is, Archimedes went home and he was mulling this problem over, and then he got in the bath and he was still thinking about the problem. And as he got into the bath, he shouted out this word, eureka is the word that he shouted out. And what he'd realized is that as he got in the bath, the level of the water in the bath moved up. And the reason the level of the water moved up is because he was displacing the water. So the volume of his body as he went into the bath was pushing the water out of the way. And he realized that if you measured the change in the depth of the liquid in the bath, you would measure the volume of his body, and that he could do the same thing for the crown that had been given to this ruler. And so he told the king, all you got to do is submerge the crown in liquid and then measure the change in depth of the fluid to figure out the volume, and then you could calculate the density of the metal that it was made of, and that way he would be able to figure out if it was really gold or not. Okay, now that basic principle, the idea of displacing a liquid, is key to understanding the idea of flotation and upthrust. So upthrust is a force exerted by a fluid on an object, displacing it. What does that mean? That means if this object, the boat, is in the ocean, then it pushes the water out of the way to take up its space. It displaces, the boat displaces the water. Now, as you displace the water, you have to push it out of the way. And you guys know from Newton's third law that if you exert a force on an object, it will exert a force on you. So when you displace the water, you push the water out of the way, and it pushes back on you. And this force of it pushing back on you is an upwards force, so it pushes up overall. In fact, it's not just an upwards force, but when we identify the upwards force, it's called upthrust, okay? And upthrust is essentially due to the volume of the liquid that you displace, okay? So I'm going to write down what we understand about upthrust. What you should know is that upthrust, I'm going to write magnitude, is equal to the weight of the fluid displaced. So if you can displace a larger volume of liquid, you will get a larger force of upthrust on you, okay? And because of this idea, we basically have a method of figuring out whether something will float or not, whether it will remain buoyant in a liquid. What do I mean? Well, upthrust, let's look at this picture, in fact, about the boat. We've got the weight of the boat acting down. Okay, and if we want this boat to float, what we need is a force up that will counteract that. And that force is provided by upthrust, okay? I'll write it as a U. So the basic idea is that we need U to be equal to W for the object to float. If the object that you place inside the liquid is less dense than the liquid, it will float. So I'll write that. If the object is denser than the liquid, it will sink. So I wonder whether some examples might be helpful for you guys, and whether they'll help you to understand the idea of perhaps fluid pressure and surface pressure. So I think I'll do one example. Get my trusty tool out here, my circle drawing tool. So it's just to help me illustrate. So I'm going to draw the scale on my barometer. Say 0, doesn't really matter what numbers are here, but I'll give them anyway. 0 to 40. And my scale is in my line from my pump. I'm going to put pump here. What we're trying to do is we are trying to figure out a relationship between, okay, I've got an inflatable, let's say it's a bag here. I've got a mass sitting on top of it. Now I know the surface area of this mass. I know the weight. And I'll write here that it's equal to m times g. And what I want to do is I want to figure out the weight of this object. Sorry, I don't know the weight. I want to figure out the weight of the object by using A and the pressure here. I'll put pressure in the gas. So the idea here is that we've got this contact area here. I'm going to illustrate that up here, okay? And we've got the pressure due to the air in the bag, the force due to it, so the force due to the pressure in the bag is counteracting the weight. So if you can figure out what the pressure is inside this airbag, okay, or cushion, and you can figure out the contact area, once you get this object to lift up, so you are balancing it, you will know that the force due to the pressure must be equal to the weight. So how would you do that? You'd say that the pressure inside this container multiplied by the surface area is equal to the force, and therefore that force would tell you the weight of this object just as it lifts up when you're inflating it. I hope that made sense. I hope it made sense, okay? We did talk about the way that pressure is exerted in fluids earlier in the topic. We don't talk about that here. We don't talk about the fact that gas particles move randomly in all directions, and when they bump into surfaces, they exert a force on them due to the collisions. But that should be understood to be part of this topic. I'm not sure why they don't include that in the topic. Okay, I hope that's useful. Please let me know if you've got any questions or if you need clarification on any of those bits. And you know, any constructive criticism or feedback is welcome, because hopefully I'll make some more of these videos. Definitely if we're not back in school sometime soon. Anyway,